Welcome to Spring LIB.
Hi, let us consider a planetary gear system. The name of the planetary gear system derives from the planetary system, where you have a gear in the center, which is known as sun gear, and then we have some gears at different points of sun gear, which are known as planet gears. And then there is an outer gear, which is called ring. So this is an outer gear. And then attached to these planetary gears is what is known as a spider. And this spider rotates as the sun gear is rotated and the planet gears are rotated. So the motion of all these gears controls the motion of the spider, and by controlling the velocity of the sun gear and the spider or sun gear on the ring, you can control the velocity of the spider. So let me just name them. This is spider and then this is ring. Okay, so now let us imagine a situation where we have this sort of situation where radius of all the sun gears equals radius of all the planet gears equals a, and radius of the ring is 3a. So all these distances are a, and then this is 3a. And then let us call these a, b, c, t, and the ring is called e. Now e is given to be stationary, and a is moving with angular velocity omega a. So let us assume it in this direction. Okay, then somebody can ask, what are various velocities of different planetary gears B, C, and D, and what is the velocity, angular velocity of this spider connecting all these points, all the centers of all the sun and planetary gears. So the spider will be something like this. Okay, to solve this problem, like in all the problems we have followed, we break the motion into translation plus rotation. And the important thing to remember that at touching points, gears have same velocity. Because if they don't, then the teeth will start eating into each other rather than smoothly gliding over each other. So using these two facts, by breaking the motion into translation and rotation, and remembering this point that at the touching points gear must have the same velocity, we can solve this problem. So let us look at A and B first. So this is the sun gear, the gear A, and it's rotating, let's say, in this direction. We know that the outer gear E is stationary, so velocity here is going to be 0, and velocity here is going to be the same as velocity of this guy, omega A. So let's draw them slightly away so that we can analyze them separately. So this is A, let's say, and this is B, and this is the touching point. I'm just drawing them separately, but these points are touching. So for the disk A, the velocity at point A, if it's rotating in this direction, which is clockwise, then this is going to be omega A, when the radius is A. And then for B, let us assume the angular velocity is omega B, and we can imagine that if A is rotating clockwise, this has to rotate counterclockwise. So the velocity at this point, as I said, has to be equal. So there will be some velocity at this point. But here we know that the net velocity is going to be 0. So because E is stationary, so here net velocity equals 0. And here net velocity has to equal omega A. And that can only be achieved if there is some translational velocity as well. So just look at this diagram again. If E is stationary and A is rotating, then that means that all these gears must also be following this sort of motion so that the E can stay stationary. So all these gears B, C, and D, the planetary gears, apart from having an angular velocity omega, they will also have a translational velocity. And the translational velocity at a point will be along the tangent to the ring because they are moving along this ring. So here, let us assume that Vt is in this direction, which you can follow by figuring out that if A is moving in a certain direction, then all the other gears will move in the other direction, and this should be the direction of Vt. So now we know that what the net velocity is going to be, but for now let's draw the separate velocities because we want to analyze these separately. So right, so for B, translational velocity is going to be same at all the points. It's Vt, 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 that's T, and then the rotational velocity, if it's moving like this, then this point has velocity omega B times A, and then this point has velocity omega B times A in the other direction, because you can just figure it out by using the right hand rule and omega cross R. And because of this cross product, the radial velocity is always along the tangent to the circle, and the direction can be figured out by this cross product of omega, and R is along this direction. So omega cross R is going to point like this. It's also intuitive to see if you have figured out or assumed a direction of omega. So if the circle is rotating like this point is moving here and this point is going to move here. Okay, so now the net motion T plus R, we know that, let's call the point which is touching B and A as point PBA. So at PBA, we know that the velocities have to equal. So omega A has to be omega B A plus the translational velocity Vt. Then at point of contact of B and E, so this is PBA, this point is PBE, this point is also PBA. Okay, but at PBE, we know that the net velocity is 0, and from this diagram, looking at Vt and looking at omega BA, the net motion is Vt minus omega BA now, because if our sign convention is x to the right, y up, then omega BA at point PBE is pointing left, so it's going to be negative. And this is because E is stationary. It's given in the problem. Right. So this gives us Vt equals omega BA. So we can call this equation 1, call this equation 2. So then 1 gives us omega A equals omega BA, and then Vt is now omega BA. So then A cancels, and we get omega B equals omega A by 2. Now, if we look at our problem, then all the planetary gears B, C, and D are in symmetric position at 120 degree. For example, if I rotate this diagram by 120 degree, D will become B, B will become C, and C will become D. So you can't tell which gear is which in this perfectly symmetric condition. So B, C, and D, since they are all planetary gears with the same dimensions, you can, without solving for them, and if you follow the same procedure, you will get the same answer anyways. So we can just say that omega B equals omega C equals omega D equals omega A over 2. Now, what is the angular velocity of spider? So this is our spider. It's going from center of A to center of B. So, and also going from center of B to center of A to center of C, and then center of A to center of D. This is our spider. And we have just figured out the VT for all of these. All of these individual gears B, C, and D. So let's call them VTB, VTC, VTG. Now, the spider doesn't have any translational velocity. The spider is just sitting at its place. So for spider, VTS is 0. And let us assume that omega TS is some omega S. So for spider, if we write translational plus rotational motion, this will give us 0 and then plus. So now we can look at the ends of all these endpoints of the spider, and this, which is actually VTB, but this is going to be, because it's rotating, it's going to be omega S. And what is this radius? This radius is sum of the two radii, A and A. So this is omega S 2A. Similarly here, omega S 2A, and here omega S 2A. And again, we can look at both these and we realize that the rotational velocity is actually coming from turning of planetary gears. So omega S 2A has to be equal to VTB, which is equal to omega B A, which is equal to omega A by 2 times A. So A cancels, and then omega S is actually omega A over 4. So this is the velocity of the spider. So we have figured out the velocity of spider and figured out the velocity of each of the planetary gear in terms of velocity, angular velocity of the sun. So this problem is solved just by assuming two things that break all the motion into translation plus rotation, and then at touching points, gears have the same velocity. Using these principles, you can solve any such problem. Thank you.